everyone, welcome to our chemistry class. Now in this video lecture we are going to deal with the thermochemistry. So far we have discussed the first law of thermodynamics, different basic terminologies used in thermodynamics, concept of work done involving an ideal gas, that is pressure volume work. So work done in isothermal process, work done in adiabatic process, different types of work done and different types of relationship between the work done and enthalpy change, energy change and heat involved during the process. Now having gone through this, we are going to deal a chemical process. So energy change in chemical transformation or chemical process, that energy change is known as chemical energetics or simply said thermochemistry. That means heat involved or heat exchange during the course of a chemical reaction. So we start with this topic, that is thermochemistry. So thermochemistry, as we have started with thermochemistry, the basic definition of this thermochemistry is heat flow during a chemical process. So heat flow during a chemical process is a chemical reaction, that is what we call as thermochemistry. Now as we have discussed earlier, whenever we carried out a chemical reaction in the laboratory, we change temperature. So because of this change in temperature, volume also varies. So temperature and volume varies during the course of chemical reaction that we carried out at laboratory. So in all this process, the pressure, that is the atmospheric pressure, remaining constant. So an energy change during a constant pressure was defined by a thermodynamic function, state function, extensive quantity known as enthalpy. So we are going to express this thermochemistry in terms of the enthalpies, means enthalpy change or the heat change during a chemical process. So now look at this. We have this enthalpy. So we have this enthalpy. So for any chemical process, we have defined this enthalpy change as the summation of enthalpies of products minus the summation of enthalpies of the reactants. So this enthalpy change, this delta S, is a difference of the summation of enthalpies of product minus reactant. So this difference can be positive or can be negative. This is the difference. Now if the difference is positive, means the summation of enthalpies of product is greater than the summation of enthalpies of the reactants, means the heat content of the product is greater than the heat content of the reactant. We say these types of reactions are known as endothermic or heat absorbing reaction. Endothermic or heat absorbing reaction. But if the difference delta H is negative, means the summation of enthalpies of product is less than the summation of enthalpies of reactants, or the heat content of reactant is greater than the product, difference comes out to be negative, and we say these types of reaction to be exothermic reaction or heat releasing reaction. So exothermic, delta H negative, endothermic, delta H positive. So if suppose the reaction is endothermic, so we write this reaction in such a way. Suppose this is reactant plus Q, that is heat, when this gives you product P. So if the heat is written on the left side, or we say this is plus heat, so the reaction is endothermic, or the reaction can also be written as, look at this, reactant changes to product minus heat. Both are defining an endothermic reaction, heat absorbing reaction. If the reaction is exothermic, the reaction is written as, we have this reactant gives you product minus plus heat. So that means after this chemical reaction, heat is produced, that is exothermic. Or the reaction can be written as reactant minus heat gives you the product P. So this is the convention in which we have to define endothermic and exothermic reactions. Now these enthalpy chains can be defined for different types of reactions. And based on the types of reaction, we define this enthalpy by various terms. So now coming to the types of enthalpy. Types of enthalpy chains. So first of all, we define enthalpy of reaction, enthalpy or heat of the reaction. Enthalpy or heat of reaction, which is represented by this term symbol delta HR. So R represents the reaction. This is heat or enthalpy change for a given chemical reaction. Now this enthalpy of reaction is defined for a complete course of reaction. So reaction should be complete. Only for that complete course of reaction we define this enthalpy or heat of a reaction. So this enthalpy or heat is defined the total heat involved during the course of a complete chemical reaction, that is defined as enthalpy of a reaction. Enthalpy change during the course of a complete chemical reaction. So I am using the term complete course of chemical reaction. So this is very specific point here. So whenever we define enthalpy of reaction, that is reaction should be complete course of a chemical reaction, and that enthalpy change is defined as enthalpy of a reaction. Suppose we have a chemical process. Let us do the chemical process. So look at this. A moles of A reacting with B moles of B, when this gives you C moles of D plus D moles of chemical product D. This is the complete course of reaction which is completely balanced. So to define all these thermochemical problems, the reaction should be completely balanced first. So without balancing the chemical reaction, we can never go for this solving problems related to thermochemistry. So for all problems related to thermochemistry, please don't forget to balance the chemical reactions. So we have this reaction. Assuming this is a balanced chemical reaction, A and B is the reactant, while small a, small b is the stoichiometric ratio of A and B in the chemical reaction. C and D is the product, and small c and d, these are the stoichiometric ratios of the product C and D formed in the chemical process. So for this, we define this enthalpy of reaction is the summation of enthalpies of products minus the summation of enthalpies of the reactant. So therefore this is equals to, so we have products C times the enthalpy of C plus D times the enthalpy of D, this is enthalpy of products, minus enthalpy of reactants, reactant is A. So A times enthalpy of A plus B times enthalpy of B. So this difference is what we call is the enthalpy of reaction. So for this individually we should know the values of enthalpies of the reactants and products present in the chemical reaction. Now this equation is also this is sometimes written as, so enthalpy of reaction is summation of Mi HP minus summation of NiHR, where Mi is the stoichiometric coefficient of the products, coefficients of product, and Ni is the stoichiometric coefficients of reactants in the chemical reaction. So stoichiometric coefficient of product is C and D, reactant is A and D. So this is what we call as the enthalpy change for a complete course of chemical reaction. Again, now look at this. This is for a general reaction. Every chemical reaction can be defined by its enthalpy change for this chemical process, which is known as enthalpy of a reaction. Now this enthalpy of reaction depends on certain factors. So let's discuss the factors on which this enthalpy of reaction depends. Factors on which this enthalpy of reaction depends. Factors on which enthalpy of reaction depends. First factor is it depends on the physical state of the reacting components. Physical state. Let's take this example. We have, look at this, hydrogen gas combines with oxygen gas. When this gives you H2O gas, so we have a complete balanced reaction. Now enthalpy change for this reaction, delta HR1, suppose this is minus X kilojoule per mole. Now the same chemical reaction can also be written as hydrogen gas plus oxygen gas giving you H2O liquid. So the physical state of the product is different here. In the first reaction we have H2O gaseous state, in the second reaction we have H2O liquid state. and this delta, let this be delta F2, which is minus y kilojoule per mole. So this x cannot be equals to y. That means when this gas is liquefied, the excess amount of energy which was present in gas will again be released. So that means minus y will always be greater than minus x. So these are two different. So these in both are enthalpy reaction, but because of the difference in the physical state of product, these enthalpy of reactions are different. So once we have this, we can easily define what is the energy change from this gases to liquid. So this difference will be energy involved from changing gases state of H2O to the liquid state of H2O. So this is the first. Second, enthalpy of reaction also depends on the allotropic forms of the reactants. Suppose for this we take this reaction, carbon diamond form reacts with oxygen gas. When this gives you carbon dioxide gas, let the enthalpy of reaction this be minus A kilojoule per mole. We can also write the same reaction, carbon amorphous form reacts with oxygen gas giving you carbon dioxide gas. Let the enthalpy of reaction for this be minus B. So now look at this, though oxygen same, carbon dioxide same, but there is a change in the allotropic forms of the reactant carbon. Carbon in the first reaction is diamond, in the second reaction is amorphous. So again now look at this A and B. This A on B may be minus or may be negative. Now this A and B, A cannot be equals to B. So once we have this A, B, again we can define how much energy is required to convert this diamond into amorphous carbon. So this is how the enthalpy of reaction depends on the allotropic forms of the reacting mix. Number third, this enthalpy of reaction also depends on the solution. For this we take this example, hydrogen gas combines with I2 gas. When this gives you Hi solution, suppose the enthalpy change for this reaction is C. Like the same reaction again here, hydrogen gas plus I2 solution, this gives you 2Hi solution. Enthalpy change with R2, that is D. Again C and D are not equal here. So again the use of solution, by use of solution, whether the reaction is carried out in presence of solution or in absence of solution, means we can change the course of reaction also. So enthalpy also depends on the use or absence of the solution for the chemical process. Now this enthalpy also depends on the temperature at which the reaction is being carried out. Temperature. So enthalpy, dependence of enthalpy on temperature is given by the equation which is known as Kirchhoff's equation. Kirchhoff's equation. So we have this heat capacity at constant pressure and enthalpy relationship. So we define this delta Cp defined as delta H divided by delta T, or we say delta H is equals to delta Cp into delta T. This is enthalpy change for the reaction, that is temperature change for the given course of chemical reaction, that is heat capacity change. Now this can be written as delta Cp is equals to delta H. So that is H at T2 minus enthalpy at T1 divided by T2 minus T1. This is the final temperature minus initial temperature. So therefore look at this, we can write down this HT2 minus HT1 is equals to delta Cp T2 minus T1. So this gives you the relationship between enthalpy change and the temperature. So once we know initial temperature, final temperature and enthalpy of reaction at initial temperature, we can find out enthalpy at the final temperature. This equation is known as Kirchhoff's equation. In this equation, delta Cp, this delta Cp change in heat capacity, this is the summation of heat capacities of the products minus the summation of the heat capacities of the reactants. So for this we need to have the heat capacities of the reactants and products. So once we define the heat capacities of reactants and products and the initial and the final temperature, and then we can easily find what is the enthalpy of the reaction at another given temperature. So this is how we correlate the temperature dependence of enthalpy of reaction. So this is a generalized term which is used for defining total heat change in any given chemical reaction. Now this chemical reaction can be of different types. Based on the types of chemical reaction, we get different names to the enthalpy of reaction. Now one thing that we have to keep in mind is sometimes all this enthalpy change is defined in standard state. Standard state. So enthalpy change in standard state we define as delta H R naught. So this naught represents the standard state. If this is not written, that is a normal state. So enthalpy change in any given standard state is written as delta H naught. Now this naught represents standard. So for this standard state, temperature is 298 Kelvin. That is 25 degrees centigrade is considered as a standard state for normal chemical reaction. Pressure is normally taken as 1 bar, or you can say 1 atm. This is the standard condition. So for any given chemical reaction, the standard condition is the reaction is at room temperature, that is 25 degrees centigrade or 298 Kelvin. If the gases are involved, the pressure of the gases are taken to be 1 bar or sometimes 1 atmosphere. So this condition is known as standard state. So we define all this in standard state, means all the reactants and the products must be at standard state of temperature and pressure. That is standard enthalpy change. Now as we have told you, yes, enthalpy change can be defined for different types of reaction. Now coming to different types of enthalpy change, or simply say types of enthalpy change. Types of enthalpy change, because we have different types of reaction. For different types of reaction, different enthalpy change names are assigned to you. So we'll take one by one. First, enthalpy of formation. Enthalpy of formation. Enthalpy or heat of formation. symbol is HF, enthalpy change or heat change during. Now this enthalpy of formation, now as the word is used formation, so this is always defined for formation of 1 mole of a substance from its constituent elements. So I repeat the sentence again. Enthalpy of formation is defined for the formation of 1 mole of a substance. Any substance, how many moles is to be formed? 1 mole. From its constituent elements. So that particular substance must be from its constituent elements only. If the formation of the substance is not from constituent elements, that energy difference cannot be defined as enthalpy of formation. That is simply an enthalpy of reaction. So this is defined only for formation of substance. So enthalpy change during the formation of 1 mole of a substance. So again I am restricting the word here. How many moles of the compound is to be formed? Only 1 mole is to be formed during the formation of 1 mole of a substance from its constituent elements. So the substance formed should be 1 mole and it should be from constituent elements. That enthalpy change is defined as enthalpy of formation. So look at this example. We have looked at this. Carbon solid combines with oxygen gas and this gives you carbon dioxide gas. So this reaction involves formation of 1 mole of carbon dioxide from carbon and the oxygen gas. Now if you look at this is a chemical reaction. A chemical reaction. Now since this being a chemical reaction, we can define this by enthalpy of reaction. So this is a general chemical reaction, so we say this is enthalpy of reaction. Now the same reaction can also be defined as the formation of 1 mole of carbon dioxide from carbon and oxygen. So this enthalpy change is defined as the enthalpy of formation of carbon dioxide. This enthalpy of formation of carbon dioxide will be equals to enthalpy of the reaction. So I hope the relation between these two is known. So for this we have to be very specific what is the reaction that is taking place. Take this reaction. We have this carbon monoxide gas plus oxygen gas, again carbon dioxide gas is formed. So carbon monoxide plus oxygen gas again gives you carbon dioxide. We say this is enthalpy of reaction because we have a chemical reaction. Now this enthalpy of reaction cannot be defined as the enthalpy of formation of carbon dioxide, though there is a formation of carbon dioxide, but definition says from the constituent elements. This is not the element. Formation should be from constituent elements. So this enthalpy of reaction cannot be defined as the enthalpy of formation of carbon dioxide. So formation, this is the formation, this is not the formation of carbon dioxide because we are not starting from the constituent elements. So this is not formation. This is the formation. Take this example. Hydrogen gas combines with I2 gas when this gives you 2HI gas. Now if you look at this balance reaction, we have a chemical reaction. For this we define this as enthalpy of reaction because this is a chemical reaction. Now the reaction also involves the formation of hydrogen iodide from hydrogen element and iodine element. So this reaction is from constituent elements, so we define this as formation. But look at this, formation says only 1 mole of the substance. Therefore, enthalpy of formation of Hi will be equals to half of the enthalpy of a reaction, because this is for complete course of reaction enthalpy change is delta H, and this is for 2 moles of Hi. For 1 mole of Hi should be half. So this is how we correlate with enthalpy of formation and enthalpy of a reaction. Again take this reaction. We have looked at this, nitrogen gas combines with hydrogen gas when this gives you 2 moles of ammonia gas. Again look at this, there is a formation of ammonia gas from nitrogen element and hydrogen element. So since this being a chemical reaction, we define this by enthalpy of reaction. But now look at this, this also involves formation of ammonia, but how many moles are formed? 2 mole. But definition says formation is defined for 1 mole. Therefore, enthalpy of formation of ammonia is half of the enthalpy of reaction. So this is enthalpy of heat change during the formation of 1 mole of a substance from the constituent elements. Now we also define as standard enthalpy of formation. Standard enthalpy of formation. Standard enthalpy of formation. Now for this standard enthalpy of formation, some very important point which is normally not mentioned in solving problems or in questions or in books, that thing we have to keep in mind is standard enthalpy of formation of the elements in their most stable state is always considered to be 0. So look at this. Standard enthalpy of formation of elements in its most stable state is always assigned a value of 0. So look at this, I repeat again, standard enthalpy of formation of elements in its most stable state is considered to be 0. So look at this, we say look at this, carbon. Carbon can exist in diamond form, carbon can exist in graphite form, this is a crystalline form, carbon can exist in fullerenes form, carbon can exist in amorphous forms. So these are different forms of carbon. Now out of this, the most stable state of carbon is graphite. Graphite is the most stable state of carbon. Most stable form. Now since graphite being the most stable form of the carbon, so standard enthalpy of formation of carbon graphite will always be 0, but standard enthalpy of formation of diamond, fullerenes, amorphous will not be equals to 0. This is the meaning of standard enthalpy of formation of elements in the most stable state, that is always 0. So again look at this, oxygen. Oxygen can exist in 2 different forms, dioxygen and trioxygen. This is ozone. Now O2 being the more stable, stable. So standard enthalpy of formation of O2 will always be 0, whereas for this ozone will not be equals to 0. Similarly, we can take some examples here. We take this element sulfur exists in two forms, sulfur rhombic and SM sulfur monoclinic. And now there is a transition between these two. The sulfur rhombic is in equilibrium with sulfur monoclinic around 96.5. This is the transition temperature. So that means this rhombic form is stable at room temperature. This is stable at high temperatures. So means at high temperature, when we heat, this rhombic form is converted into monoclinic form. So out of these two, this rhombic form is more stable. So this being the most stable, so standard enthalpy of formation of rhombic sulfur will be 0. This is the meaning of standard enthalpy of formation of elements in the most stable state being 0. Take this, we look at this bromine. Bromine in room temperature, bromine is a non-metal that exists in liquid state. Now the same bromine can also be in gaseous state. So bromine being liquid at room temperature, this is more stable. So this is more stable. So enthalpy of formation of bromine liquid will be 0. So this is the standard enthalpy of formation. So we have to keep in mind during the course of solving problems, if the standard enthalpy is reused and this enthalpy of formations are mentioned, then if there is any element which is the more stable state in the room temperature, for those enthalpy of formation will always be 0. Now if enthalpy of formations of the reactants and products are mentioned, then how to find the enthalpy of the reaction from enthalpy of the formation of reactants and the products? So the relation between these two is enthalpy of a reaction is equals to the summation of enthalpies of formation of product minus the summation of enthalpies of formation of a reactant. That means if the enthalpies of formation of the reactants and the products are mentioned to you, then we can easily define what is the enthalpy of a reaction. So this is enthalpy of reaction in terms of the enthalpies of formation of products and reaction. Under standard condition, this can be written as standard enthalpy of reaction is equal to summation of the standard enthalpies of formation of products minus summation of standard enthalpies of formation of a reactant. This is under standard condition when all the reactants and products are under standard conditions of temperature being 298. If gases are involved, the pressure of the gas should be at 1 bar or 1 atm pressure. So this is how we correlate enthalpy of reaction from enthalpies of the formation of the reactants and the products. So next enthalpy is enthalpy of solution or enthalpy of dissolution. Now this enthalpy of solution is defined as the enthalpy change when a substance is dissolved in excess amount of solvent such that further addition of solvent does not bring about any change in the enthalpy. So this is what we call as enthalpy of solution. So defined as enthalpy change when 1 mole of a substance is dissolved in excess of solvent. I repeat again, enthalpy change when 1 mole of the substance is dissolved in excess of solvent such that further reaction does not bring about any change in the enthalpy. That is what we call as enthalpy of solution. Now this is enthalpy of solution depends on the solvation energy and the ionization energy. Suppose look at this. This enthalpy of solution, delta H solution, this depends on two factors: ionization or dissociation, and the second is solvation. Take this. We have look at this. Suppose we have this HI is being dissolved in water. When this gives you HI solution. So when this HI is dissolved in solution, this gives you H plus ion surrounded by water plus I minus surrounded by water. That is equated H plus ion, equated I minus sign. Now look at this. In this process, look at this. HI breaks into H plus ion, I minus, and finally this IH plus ion or I minus is surrounded by a layer of water molecule that is known as the solvation. So enthalpy change for this, that is known as enthalpy of solution. So this enthalpy of solution is equals to enthalpy of ionization plus enthalpy of solvation. Here the solvent is water, so we can say this enthalpy of hydration, because first HI is to be ionized to give a H plus ion and I minus ion, and again this I minus ion will goes into solution when this will be surrounded by a layer of water molecule, that is solvent, and this I minus will again be surrounded by a layer of solvent molecule. So this depends on this enthalpy of ionization and solvation. Now ionization means we have to break the bond. So enthalpy of ionization is always positive, that is endothermic, whereas solvation process or the hydration process is always exothermic, energy is released. So this is a combination of two terms. One term is endothermic, the other term is exothermic. Based on this enthalpy of solution may be positive, may be negative. That means this may be exothermic or endothermic. So this enthalpy of solution is exothermic if delta H solvation is greater than delta H ionization, or this dissolution process will be endothermic if enthalpy of ionization is greater than enthalpy of hydration or solvation. So simply saying, when a particular substance, 1 mole of substance is dissolved in excess amount of solvent, what is the heat involved or what is the heat change? This depends on two factors, ionization and the solvation. Means the compound will be first ionized, and after this the cation anion will be surrounded by a layer of water molecule, that is known as solvent, and during this solvation how much energy is involved. So ionization is breaking of bonds. So breaking of bonds, we have to supply energy, that is always endothermic. Solvation, when a particular ion is surrounded by a layer of solvent molecule, in most of the case we use water as a solvent, so that is known as hydration. So solvation or hydration is always exothermic, energy is released. So one is endo, the other one is exo. The combination of these two may be endo or exo depending on the values of this endo or exo. This is what defines as enthalpy of solution or simply enthalpy of dissolution. Next enthalpy is Enthalpy of dilution. So as we know, dilution is changing the concentration of the solution from higher concentrated solution to the lower concentrated solution. So by addition of excess quantity of solvent. So during this dilution process, how much energy is involved, that is known as enthalpy of dilution. So this is defined as enthalpy change when 1 mole of solute undergo change in concentration changes its concentration by adding water. That means on changing concentration from one higher concentration to the lower concentration, how much energy is involved? That change in concentration is what we call as dilution, and energy change during this dilution process is known as enthalpy of dilution. Then we have enthalpy of hydration. Enthalpy of hydration. Now this enthalpy of hydration is defined for those processes in which anhydrous salt combines with water to give you hydrated salt. Enthalpy change when 1 mole of an anhydrous salt enthalpy change when 1 mole of an anhydrous salt is converted to hydrated salt by reaction with required amount of water. That enthalpy change is known as hydration enthalpy. Look at this. Copper sulfate anhydrous. This reacts with 5 water molecules. When this is converted into, this is solid anhydrous, reacts with 5 water molecules. When this gives you copper sulfate pentahydrate. This is again solid. So this is known as hydrated salt. So we are converting this anhydrous salt into hydrated salt. So during the course of this formation of hydrated salt, how much enthalpy is changed? That is known as enthalpy of hydration. Similar, look at this. We have magnesium sulfate anhydrous reacts with 7 water molecules. When this gives you magnesium sulfate heptahydrate, this is hydrated salt. So what is the enthalpy change during this hydration? That is what we call as enthalpy of hydration. Means 1 mole of anhydrous salt is to be converted into hydrated salt. So during this we react with a required number of water molecules, and this process is being known as hydration. Enthalpy change is known as enthalpy of hydration.